this is a discussion of the 4 quantum numbers. Now you already know the electron configuration. So for example, if I wrote 1s2, 2s2, 2p2, that would obviously be element number 6. And if we go to the periodic table, I'm trying to find mine, it would be carbon. So this would be the electron configuration for carbon. And that's carbon in the ground state. You notice that we have all the lowest energy levels filled. We fill the 1s, then we fill the 2s, and then we fill the 2p. All 6 of those electrons occupy different regions of space, and that's exactly what we want to have happen. 2 electrons can't occupy the same exact space. So this discussion of 4 quantum numbers helps us figure out exactly where those electrons are at a given time. So let's go through the 4 different quantum numbers. We already talked about n, which is the principal quantum number. And that is the large number that you see right here, the 1 or the 2. So 1, 2, 3, etc. And if we're thinking about relating it to the periodic table, that of course relates to the level of the periodic table. Loosely, at least in terms of making sense of it and electron configuration. So principal quantum number really is how far the electrons are away from the nucleus. Electrons on level 1 are closer to the nucleus than electrons on level 2 and electrons on level 3. That also gives rise to different properties of atoms, for example. So an atom that has 5 levels of electrons that are occupied has a less pull on those outer shell electrons than electrons that might be on level 1. So the principal quantum number helps us figure out valence and other things. So in this carbon atom, you can see that there are electrons occupying the first and the second principal quantum number. Then the second quantum number is L. L is called the angular momentum quantum number. And L goes from 0 to n minus 1 for each value of n. And this relates to the shape of the orbitals. We would have called it S, P, D, and F. The next quantum number is m sub L. M sub L is the magnetic quantum number. M sub L has a value between L and negative L, L being the angular momentum quantum number, including 0. This is related to the orientation of the orbital in space relative to the other orbitals in the atom. So in a p sublevel, it would kind of be like x, y, z. And then finally, the last quantum number is the m sub s, which is the spin. Magnetic spin quantum number. And that's either positive 1/2 or negative 1/2. And this has to do with the orientation of the electrons either moving clockwise or counterclockwise, because if something is moving clockwise and something else is moving counterclockwise, they're less likely to collide with each other. And remember, if 2 electrons are going to have to occupy the same angular momentum quantum number and the same magnetic quantum number, they need to not collide. And so designating positive 1/2, negative 1/2 allows us to differentiate between the particular electron we're talking about. So let's figure out how these four quantum numbers, the n, the l, the m sub l, and the m sub s, would represent an electron in an atom. And we're going to use carbon as our example. So when I think about this, I'm pretty good with the electron configuration, and I can always figure that out from the periodic table. So I don't have to memorize any kind of rules, or, some books show a way to use arrows and the order of filling, and then you can figure out the electron configuration that way. But because the periodic table is set up so perfectly for that, I don't need to memorize too much. So the four quantum numbers I can derive from my knowledge of the electron configuration. Let me explain what I mean by that. Now, the principal quantum number is something we talked about in intro anyway. So 1, 2, 3, 4. Those big numbers, the ones I put an arrow under up here, is the principal quantum number. I got that. The L relates to the orbital. So in other words, you see it says from 0 to n minus 1. Well, I don't really think about it like that. I think of L as representing S, P, D, and F. So whenever I think about S, I know it's going to be 0. This is going to be 1, 2, and 3. So F is going to be 3. So in other words, whenever I'm talking about a 3p sublevel, then I know the first two quantum numbers are going to be 3, 1. If I'm decoding that into a series of 4 numbers. So that's how I get L. Then I also know m sub L, because when we do the orbital diagram, that's the pictures with the boxes, I know that S has one box. P is a triple box. D is something with 5 boxes. And F is something with 7 boxes. 1, 2. And again, I can figure that out from the periodic table. So if I come to D, 4D, I know that D is going to have 5 boxes, and then I can fill the correct electrons in there. Well, you can notice up here the magnetic quantum number goes from L and negative L. So this is how I do it. I know, for example, that an S sublevel, this one is, notice S I'm putting on this line, then P, then D, then F. I always think of the center box as the 0 starting point. Okay, so in an S sublevel, it's always going to be m sub L of 0, because there's only one box. For the P, the center box is 0, and this is plus 1, minus 1. Whoops, almost made that negative. Sorry about that. In a group of 5, plus 1, plus 2, negative 1, negative 2. So I'm starting in the center, and I'm going out in both directions, thinking almost like a number line. Plus 1, plus 2, plus 3, negative 1, negative 2, negative 3. So if I wanted to, for example, going back to this, and I wanted to say 3D2, and I wanted to talk about the second electron in the box, the last electron, if you will, going in ground state order. I could say, if I wanted to use my 3 quantum numbers, I would say 3, 2, and then thinking about my D2, what that would really mean if I had a picture of it. Oops, not exactly perfect. This D2 would really represent that electron right there. I've got a lot of arrows. Sorry about that. So you notice if this is my 0, then this is the negative 1 spot. So the 3 quantum numbers that I'm referring to here are 3, 2, negative 1. So I've kind of decoded it in number fashion, as opposed to saying 3D2, I'm saying 3, 2, negative 1. And then the last, m sub s, That's the easiest one ever, because it's either a positive a half or negative a half. Now, positive 1/2 means the upward arrow, negative a half is the down arrow. So in the previous box, it's not only 3, 2, -1, it is positive 1/2. Now, eventually, if I had something like 3d7, right, and I wanted to discuss the 7th electron that has been filled, that picture would look like 1, 2, 3, 4, 5, 6. I have too many boxes. Well, that's my problem. I need 5. I was thinking F. 1, 2, 3, 4. Okay, good. So D7 would be 1, 2, 3, 4, 5, of course, 6, 7. So that means I am trying to discuss that one right there. So the 4 principal quantum numbers that would relate to it are 3, 2, -1, -1/2. Now notice, this answer and this answer both describe the electrons in box number 2. But you'll notice they have different sets of numbers. At least the last number is different. And remember, Pauli exclusion principle says no 2 atoms can have the same 4 principal quantum numbers. So we can describe things by their quantum numbers. So let me scroll down a bit, and I'm going to let me move this up so we can see some of the ideas here. Let's say I wanted to do that carbon one. Remember, carbon is 1s2, 2s2, 2p2. Now obviously there's 6 electrons. So that means technically there are 6 sets of 4 quantum numbers that could represent all 6 electrons. So what I'm going to do is I'm going to go through and we're going to describe every single quantum number for every single electron. So let's start with the first one, and maybe to make it easier, I'm going to translate this into orbital notation. You don't have to, but for this discussion I thought it would be easier. Alright, so we're going to take the very first electron you see there. Obviously that's principal quantum number 1. It's in an S sublevel, so S is always 0. It is the S, M sub L is in an S, so it has to be 0. And it's positive 1/2. That describes the first electron. The next one is 1, 0, 0, -1/2, because you have to fill the S sublevel before you go on. So that would describe that downward facing arrow. The next one, 2, 0, 0, positive half, and 2, 0, 0, -1/2. Again, this would be those two. So it's pretty easy when it's an S sublevel. It always is 0, 0. There are some sets of 4 quantum numbers that could never be used. For example, you could never have 1, 1, 1, +1/2. Oops. This would not be allowed because you couldn't be in level 1 P. You don't have 1p. It doesn't exist. So this is wrong. So even though you can list 4 different quantum numbers, it might not be valid. So that is probably some of the homework type questions you might see, ones that are incorrect, or they might ask you which ones are incorrect. Perfect multiple choice questions for the exam because you don't need a calculator. So far we have discussed the first 4 electrons. Now we're moving on to the second grouping, or the last 2. So principal quantum number 2. Now we're describing this first one here. We know it's in a P sublevel. So P is 1. We also notice, thinking 0, -1, +1, it's in the first box, -1, and it's facing upright. So 2, 1, -1, +1/2. It isn't very difficult, but if you've never seen it before, it could be a code you've never known. So hopefully this discussion is helpful. And then the last electron number 6 would be 2, 1, 0, positive 1/2. So that would be the 6 electrons in carbon. And they all have 4 numbers each, or 24 total. So you can see if you were going to do this for a large atom, it could take a whole lot of time and a whole lot of numbers. Not very difficult, but you do have to follow the pattern. So I'm going to flip and I'm going to check out a question, and I'm looking in the back of the textbook, and I'm going to say a question like this one as a little bit of a practice. And it says, which of the following sets of quantum numbers are not allowed in the hydrogen atom? For the sets of quantum numbers that are incorrect, state what's wrong in each set. Okay, so we have n equals 2, L equals 1, m sub L equals -1. So what that means is we are going to think, can this arrangement exist? Now, even though the directions say allowed in the hydrogen atom, you might think, oh, they're only talking about hydrogen in the ground state. They're talking about just one electron, because of course things can be in the excited state. All right, so to decode this, I would have to say, level 2, thinking back to electron configuration, L, remember, is P. And m sub L, the next number, has to do with the boxes. So in the P, we have 2p -1. Can that happen? Can we have a 2p1? Can something be in 2p1 in that box right there? Is that possible? I think it is allowed. So this one is okay. Let's check the next one. N equals 1, L equals 1, m sub L equals 0. So again, I'm decoding it. Okay, 1. L sub 1 is P, and m sub L with the P is going to be in the center box. Now, can that be? Can we have 1p1 being in the center box? The fact that it's in the center box really doesn't matter, because technically in the P sublevel you could fill the second box before the first because they're of equal energy. That's not the problem here. The problem is there's no such thing as 1p. So this is one that is not allowed. Now let's try another one. N equals 1, L equals 0, m sub L equals 2. Okay, so here we go. So 1s. Now, the electron in the 1s is allowed, so that's fine. But now we have m sub L of 2. M sub L of 2 would have to be a box that has 5 squares, because you have to be 0, +1, +2, and this is -1, -2. So we're talking about something right here, maybe up or down. It doesn't have an m sub s number. So can that be the case with 1s? 1s1, could 1s1 be there? No, it can't be. So we'd have to have, if you had 3 principal quantum numbers, you could say 1, 0, 0.